Hello and welcome to this new tutorial. This one is going to be exciting because this is the beginning of the whole construction of the MDN RNN model. Because indeed our first phase here is to build the RNN part of the MDN RNN model, that is exactly this part here. We have these two components, the RNN which will get the inputs, meaning the last hidden state, the last action plate and the last latent vector z, and which will return as output the new hidden state and the deterministic latent vector, which will then be stochastically sampled from this probability density function pz, which is nothing else than this probability of the next latent vector z conditionally to the last action plate, last latent vector and last hidden state. So right now we're about to build this part, and we will build that in 3 steps. First step will be to build the LSTM cell inside the RNN. Then second step will be to add the dropout to 3 elements inside the RNN, which will be first the recurrent dropout inside the LSTM cell, then the input dropout for the input, and the output dropout for the output layer. And then third and final step, we will wrap everything, meaning the LSTM cell connected to the input and the output, and to which we add the dropout regularization, into the whole recurrent neural network model. And this is the general blueprint of building a recurrent neural network with TensorFlow. So whenever you want to build the same for another application, well, you can just follow again this blueprint in 3 steps. First, you build the LSTM cell. Second, you add the dropout. And third, you wrap everything into the whole RNN model. And that's why I've prepared for you the links in the TensorFlow documentation, which will contain all the tools for these 3 steps. So remember, the first step to build the LSTM cell will be done thanks to the layer norm basic LSTM cell class by TensorFlow. Then to add the dropout, we will use the dropout wrapper for the inputs and the outputs. And then, however, to add the dropout for the LSTM cell, we'll just use that dropout key prop parameter here. And then last step, to wrap the whole thing, that is the LSTM cell connected to the inputs and the outputs plus the dropout added to them, we will use the dynamic RNN function, which will indeed take as input the LSTM cell plus the input, to which we will have the dropout added optionally. And then of course this will return the outputs. Alright, so let's do this. Let's do these 3 steps, and we're going to start with the first one, meaning we're going to build the LSTM cell with the right number of units. So I'm going to copy all this because we will create this LSTM cell as an object of the layer norm basic LSTM cell, and therefore back on Python, here we go. Let's introduce a new variable here that we'll call cell underscore fn for function, because it's going to be the object of this layer norm basic LSTM cell class, but we won't add the arguments yet because we will do this when adding the dropouts with some if conditions. Why if condition? That's because we want to give us the options actually to add these dropouts. So we might, activate the dropout on the LSTM cell, but deactivate it on the input or the output. So we want to give us these options, and the way we're going to do this is by creating 3 variables. Each one will be a Boolean, true or false, for whether or not we're going to activate each of these 3 dropouts. So speaking of these Boolean variables, let's create them right now. The first one will be for the recurrent dropout added to the LSTM cell, and we're going to call that Boolean variable use recurrent dropout, which will be equal to false if, and now to understand we need to go back to this layer norm basic LSTM cell documentation, because indeed among the arguments of this class we have this dropout key prop parameter, which will be a number between 0 and 1, and which will basically be the rate of units inside the LSTM cell that will be kept activated, meaning that won't be dropped out or deactivated during the training, because that's what dropout is about. This is a regularization technique which allows to avoid overfitting by deactivating some of the neurons or some of the units inside the LSTM cell in a parameter update step. And so this is very effective, and that's why right now we want to add the dropout to indeed do some regularization to avoid overfitting. And so what I was saying is that this dropout keep prop parameter is a number between 0 or 1, and therefore if it is equal to 1, that means that we're going to keep all the units activated inside the LSTM cell during the training, and therefore dropout won't be activated. So what we're going to do now is, back on Python, we're going to deactivate dropout, meaning we're going to set this use recurrent dropout to false if one of our hyperparameters, which is in our self.hps hyperparameter object, and which is called use recurrent dropout, is equal to 0. Because indeed, if this is equal to 0, that means basically that this keep prob dropout parameter will be equal to 1, meaning that we won't apply any dropout. And so, if that is equal to 0, use recurrent dropout will be equal to false, and that will be the option where we don't want to activate dropout for the LSTM, the recurrent dropout. Alright, and then, however, else, if that same use recurrent dropout parameter is different than 0, then in that case, dropout will be activated. And so, we'll set that use recurrent dropout boolean variable to true. And perfect, now we're going to do exactly the same for the other ones, meaning for the other two dropouts. The first one for the use input dropout, which will be same false if the use input dropout from our HPS hyperparameter object is equal to 0, and else it will be equal to true, meaning that we will have indeed dropout activated for the input. And then lastly, we can actually copy this, use input dropout, because now what I want to do is exactly the same for the output this time. So I'm going to replace the in here by out and the in here by out again, so that if this use output dropout parameter is equal to 0, then use output dropout will be equal to false, meaning we won't have dropout activated for the output. And else, if it is different than 0, then the dropout for the output will be equal to true, meaning that we will activate dropout for the output with a certain keep prop parameter, which no worries, we will specify right after this. So, first thing done, we basically created some booleans which will allow us to give us the options to activate dropouts for each of the three elements, input, output, or LSTM cell. And now, speaking of giving us these options, well, let's implement that right away. And we're going to do that with some if conditions, starting with the first one. If our use recurrent dropout boolean variable is equal to true, which we don't have to specify because true is the default value of a boolean, then in that case, what will we do? Well, if this use recurrent dropout is equal to true, that means that we want to activate dropout to the LSTM cell, and therefore what we'll do is create a new variable which will be our final LSTM cell, and which will be that cell fn object variable from the layer norm basic LSTM cell class by TensorFlow, to which we will input the right arguments so that we can have the dropout. And speaking of this argument, you might guess that the one which will specify that indeed we want some dropout activated will be this one, dropout keep prob, which will therefore be a number below 1, because 1 means that we're keeping all the units activated. Alright, but first, let's implement the other arguments, starting with number of units. And we're going to get these arguments with, again, our hyperparameter object HPS, which contains basically all the hyperparameters of the recurrent neural network. And the name for the number of units is not going to be numunit, but the author chose to call it RNN size, right? The number of units in the LSTM cells. And then let's take care of the other arguments. So it won't be this one, or that one, because we're going to keep the default values. However, we're going to give a different value to this one, which is basically the option of normalizing the layer in the basic LSTM cell. And the default value is true, but we will give us the option to have true or false. And the way we're going to do this is by entering layer norm here, which is just the name of the argument. And then what we can do is create another option as the ones we created here, but this time for the normalization. So for example, let's say that layer norm is going to be use layer norm, and this use layer norm is going to be another boolean as what we did here, only to create it, we're just going to replace use output dropout by use layer norm, and then same use layer norm right here, because indeed use layer norm is actually another hyperparameter inside our HPS hyperparameter object. And so here, just doing this new line of code gives us a new boolean which will be equal to false if the use layer norm in the hyperparameters is equal to 0 and true otherwise. All right, perfect for that new argument. And then, of course, now is the time to specify that we indeed want dropout, because this is indeed the condition where use recurrent dropout is equal to true. So we're going to get that final dropout keep prop parameter for the LSTM cell. So I'm copying this, and here we're going to paste that, and we're going to set that equal to another parameters of our hyperparameters object, which is called the recurrent dropout prob. All right, so that's the name for that exact keep prob parameter, that number between 0 or 1, and which will give basically the rate of the unit that will be kept activated inside the LSTM cell. All right, so all good here. We basically added the dropout for the LSTM cell, the recurrent dropout, and now else, meaning if use recurrent dropout equals false, then in that case, we're going to do exactly the same, getting the final cell, but this time, of course, without the dropout. All right, very simply, because by default, the dropout keep prop parameter is 1, meaning that we're keeping all the units activated in the LSTM cell, and therefore that means that we don't add any dropout. All right, now let's do the same for the other two dropouts, for the inputs and the outputs. And so to do that efficiently, I'm going to copy this first if, because this time we're not going to have an if-else condition, but just an if condition. And the reason is that we're going to add the dropout with this dropout wrapper class, which is only the class used to add the dropout for both the input and the output. And so we could add the dropout for both the input and the output at the same time, but since we want to have the option of adding, for example, a dropout to the input but not to the output, or the other way, well, we will do two if conditions here, inside which we will have the separate option to add the dropout to the input and to add the dropout to the output. So here I'm going to replace use recurrent dropout by use input dropout, and here I'm going to replace use recurrent dropout by use output dropout. And then of course now we're going to remove that, because that was the previous way of how we could add the dropout to the LSTM cell, but now we're going to use another way, which will be the dropout wrapper class by TensorFlow. And therefore here, to add the dropout to the input, well, of course, we're going to use this dropout wrapper class. And so let's get back to the documentation, this one. Now we're going to take all this, which is the name of the class and all the path to get it from TensorFlow, and inside this class we will input the right arguments, which will allow to activate dropout for the input. And so, as you can see, the first argument is the cell, and which is exactly the cell we created here, and which was updated with dropout activated or not, whether we want to use the recurrent dropout. And so that's this cell here. Then the next argument, here we go, is the one we're interested in right now, to add the dropout to the input. And so we're going to input this argument, which I'm going to copy here, input keep prop. By default, this argument is equal to 1, meaning that we're keeping all the input units activated. But since right now we want to use dropout, that means that we want to have some other value, between therefore 0 and 1 excluded. And this value, we will get it again from our hyperparameter HPS variable object, from which we're going to get that exact input keep prop parameter, which has the following name, input dropout prop. And that's it. And of course, we don't need an else here, because if else, this is equal to false, then the cell will just keep being this one, with either the recurrent dropout activated or deactivated, because the only argument we had to input here was for that input keep prop value, which is equal to 1 by default. And now let's do the same for the output dropout. And therefore, I'm going to take that again, copy it, paste it here. And of course, I'm going to replace here input by output, and same here, input by output. And here we go, Now we've just implemented the options to add separately some dropout to the LSTM cell, the input and the output. So that's a good thing done. The second step in the process of building a recurrent neural network, I want to precise that here, this is the general blueprint of how we can build a recurrent neural network with an LSTM cell and dropout activated. So if you want to use that for another application, you can still follow this process. And now the next step is to create a new object variable, which will be that LSTM cell with dropout added or not. And to do this, well, very simply, we just need to create a new object variable which we'll call self.cell, and which will be, of course, equal to that LSTM cell that we've just created with these optional dropouts. And so self.cell equals cell, and now congratulations, you implemented an LSTM cell with an optional dropout inside a recurrent neural network. And speaking of recurrent neural network, that leads us to the next step, which is to wrap all that with the inputs and the output inside the whole recurrent neural network. And to do this, well, we're going to use our final tool, which is the dynamic RNN function. So let's do that final big step in the next tutorial, and until then, enjoy AI.